Imagine for a moment that everything you see in the night sky, every star, every galaxy, every cluster of light stretching across the cosmos, is nothing more than decoration on the surface of something far larger, something invisible, something that comprises 95% of all matter in the universe. In 2014, astronomers captured an image that shouldn't exist. Between two galaxies separated by hundreds of thousands of light years, they photographed a bridge. Not a metaphorical bridge, but a physical structure of dark matter connecting distant islands of light like cosmic filaments in a spider's web. This wasn't supposed to be possible. For decades, we've known that galaxies aren't scattered randomly through space. They cluster. They form chains. They organize themselves along invisible pathways we cannot see. But what we're discovering now suggests something more profound. The universe has bones, a skeleton made of dark matter stretching across billions of light years. And everything we can see, every star, every planet, every atom in your body, exists within the flesh of this cosmic web. What if galaxies don't simply exist in space, but rather they mark the intersections of something far more fundamental? What if the universe isn't expanding into emptiness, but growing along predetermined pathways laid down in the first moments after the Big Bang? Today, we journey through evidence that challenges everything we thought we knew about the structure of reality itself. Prepare yourselves. We begin. In 1989, astronomer Margaret Geller stood before a map that would change cosmology forever. She and her colleague John Huckra had spent years measuring the distances to thousands of galaxies, plotting each one's position in three-dimensional space. When they finally stepped back to view their creation, the first large-scale map of cosmic structure, they saw something that made no sense. The galaxies weren't scattered randomly through space, as theory predicted. Instead, they formed an enormous pattern. Chains, walls, vast empty regions called voids. The galaxies traced out what Geller immediately recognized: a cosmic web. "It looks like a slice through a sponge," she told the assembled press. But this sponge was 500 million light years across. To understand why this discovery was so troubling, we need to go back to the beginning. In the moments after the Big Bang, the universe was nearly perfectly smooth, just a hot, dense soup of energy and matter, expanding in all directions. The cosmic microwave background, the afterglow of creation itself, shows us this smooth, early universe. Temperature variations across the entire sky amount to just 1 part in 100,000. How did we get from that smooth beginning to the intricate web of structure we see today? Think of it this way. If you poured water onto a perfectly flat surface, it would spread evenly in all directions. But if that surface had the tiniest imperfections, microscopic bumps and valleys, the water would begin to pool in certain areas. Those pools would grow deeper, pulling in more water through gravity, eventually creating puddles, then lakes, then vast reservoirs separated by dry land. This is essentially what happened to matter in the early universe. Tiny quantum fluctuations, random variations in density, no larger than 1 part in 100,000, became the seeds for everything we see today. Regions slightly denser than average pulled in surrounding matter through gravity. Over hundreds of millions of years, these dense regions grew, while the spaces between them emptied out. But here's the puzzle. Computer simulations of this process predicted that matter would clump together gradually, forming scattered clusters. Instead, we see organization, we see structure, we see the web. In the decades following Geller's discovery, astronomers mapped more and more of the universe. With each new survey, the cosmic web became clearer and more disturbing. The Sloan Digital Sky Survey mapped over 1 million galaxies. The 2DF Galaxy Redshift Survey added hundreds of thousands more. Each time, the same pattern emerged. Galaxies are organized along filaments stretching across hundreds of millions of light years, meeting at dense nodes where thousands of galaxies cluster together. The largest structures ever discovered bear names that hint at their scale. The Sloan Great Wall, measuring 1.4 billion light years across. The Hercules Corona Borealis Great Wall, stretching an incomprehensible 10 billion light years, so large that light hasn't had time to cross it since the universe began. But the most troubling discovery wasn't the filaments themselves. It was what they're made of. When astronomers calculated the mass needed to hold these structures together, the numbers didn't add up. The visible matter, all the stars and gas we can see, accounts for only a tiny fraction of the gravitational force required. Something else had to be there, something massive, something invisible, dark matter. The cosmic web isn't made of stars and galaxies. Those are merely decorations, lighting up the surface of something far larger. The true structure of the universe is built from dark matter, a substance that doesn't emit light, doesn't absorb light, and barely interacts with normal matter at all. It only reveals itself through gravity. Imagine a city at night from an airplane. You see the lights, buildings, streets, cars. But those lights only show you where people are, not the geography underneath. The mountains, the rivers, the valleys, they're all there in the darkness, shaping where the city could grow, but remaining invisible themselves. That's our universe. We are the lights, scattered across the surface of an invisible landscape. But the evidence forces us to confront an uncomfortable possibility. If dark matter forms the skeleton of the universe, and if that skeleton was laid down in specific patterns during the first moments after the Big Bang, then the cosmic web might not be a structure that evolved randomly. It might be the fundamental architecture of reality itself, a framework that determined where galaxies could form, where stars could ignite, and ultimately, where life could emerge. Everything we can see exists because of something we cannot. Accumulating evidence. Part A. Observable signatures. The first direct evidence for dark matter filaments came from an unlikely source: bent light. In 2012, a team led by Jörg Dietrich at the University of Michigan detected something extraordinary between two galaxy clusters called Abel 222 and Abel 223, separated by nearly 500 million light years. Using weak gravitational lensing, a technique that measures how invisible mass bends the light from distant galaxies, they mapped the distribution of dark matter between the clusters. What they found was a bridge, a filament of dark matter, weighing approximately 100 trillion times the mass of our Sun, physically connecting the two clusters like a cosmic highway. This was the first time anyone had detected dark matter in intergalactic space. The invisible web had become visible, but this represents just one piece of a much larger puzzle. Scientists discovered that these dark matter filaments have structures of their own. They're not smooth highways, but rather twisted bundles, like cables made of smaller threads. High-resolution simulations revealed that each major filament contains hundreds of smaller subfilaments, which themselves contain even smaller threads. It's structured all the way down. The Illustris project, one of the most detailed computer simulations of the universe ever created, modeled the evolution of a cubic region of space 350 million light years on each side. The simulation tracked 12 billion particles from shortly after the Big Bang to the present day. What emerged was breathtaking: a fractal web of dark matter, with structure repeating at every scale from millions of light years down to scales of individual galaxies. In 2019, researchers made another stunning discovery using the Hubble Space Telescope. They studied the light from distant quasars, brilliant beacons powered by supermassive black holes, as it passed through the cosmic web. As that light traveled through dark matter filaments, it encountered pockets of normal matter, gas clouds enriched with elements forged in ancient stars. These gas clouds revealed something remarkable. The filaments aren't empty. They contain vast reservoirs of warm gas, heated to temperatures of 100,000 degrees, threading through the dark matter like blood through veins. Scientists calculated that these filaments contain more normal matter than exists in all the galaxies combined. Half of all the atoms in the universe reside not in stars or planets, but in the space between galaxies, trapped within the cosmic web. This warm gas had been theoretical for decades, but we finally found it hidden in the web's architecture. The evidence extends beyond direct observation into the realm of cosmic archaeology. In 2018, astronomers noticed something peculiar about the way galaxies spin. As galaxies orbit around each other within a filament, they tend to rotate in the same direction, an alignment that persists across millions of light years. This shouldn't happen if galaxies formed independently. The probability of this alignment occurring by chance is less than 1 in a billion. Something about the cosmic web itself is influencing how galaxies rotate, suggesting that the web structure actively shapes galaxy formation and evolution. The implications are staggering. Galaxies aren't just passive inhabitants of the cosmic web, they're products of it. But perhaps the most disturbing evidence comes from the voids, the vast empty regions between filaments. These cosmic deserts, some stretching 300 million light years across, aren't completely empty. They contain a handful of isolated galaxies that astronomers call void galaxies. These galaxies are different. They form stars more slowly. They contain different ratios of elements. They evolve along different pathways than galaxies within filaments. It's as though the environment of the cosmic web fundamentally alters the nature of galaxies themselves. In 2020, a study of 10,000 void galaxies confirmed something remarkable. Galaxies remember where they formed. Even if a galaxy later migrates into a filament, it retains characteristics of its void origins. The cosmic web doesn't just determine where galaxies form, it permanently imprints their properties. The architecture shapes the inhabitants. Part B: Deeper implications. The most remarkable discovery involves the cosmic web's role in feeding supermassive black holes. In 2015, researchers using the Very Large Array Telescope in New Mexico observed cold gas streams flowing along dark matter filaments directly into the centers of massive galaxies. These streams, called cold flows, bypass the hot gas atmospheres surrounding galaxies and deliver pristine material straight to the supermassive black holes lurking at galactic centers. This solved a long-standing mystery. How do supermassive black holes grow so large so quickly? The answer lies in the cosmic web itself. The filaments act as feeding tubes, channeling matter across millions of light years directly to where it's needed. But here's where it gets strange. The rate at which these filaments feed black holes appears to be calibrated. Too much inflow, and the black hole would grow too quickly, destroying its host galaxy through violent feedback. Too little, and the black hole would starve. Instead, we observe a delicate balance, almost as if the cosmic web self-regulates. In 2017, the Dark Energy Survey detected something that seemed to contradict established physics. They measured the alignment of galaxy shapes across hundreds of millions of light years and found correlations that were stronger than dark matter alone could explain. Something else was influencing the web's structure on the largest scales. That something is dark energy, the mysterious force causing the universe's expansion to accelerate. And it's in direct competition with the cosmic web. Dark energy tries to pull space apart. The cosmic web tries to pull matter together through gravity. On small scales, the web wins. On large scales, dark energy wins. But there's a critical scale in between, around 300 million light years, where these two fundamental forces are perfectly balanced. This scale determines the maximum size of cosmic structures. Nothing larger can form because dark energy tears the web apart. The cosmic web has boundaries, and dark energy defines them. Recent discoveries reveal patterns in the cosmic web that shouldn't exist according to our current understanding. In 2021, astronomers analyzed the three-dimensional positions of 2 million galaxies from the Baryon Oscillation Spectroscopic Survey. They found that the cosmic web contains acoustic oscillations, ripples in space from sound waves that propagated through the early universe. These ripples created a characteristic pattern. Galaxies are slightly more likely to be found 500 million light years apart than at other distances. This standard ruler appears throughout the universe with remarkable consistency. But here's the puzzle. These patterns are too perfect. The universe is 13.8 billion years old, but light has only had time to travel 46 billion light years in any direction, the size of the observable universe. Yet the cosmic web shows the same patterns and structures across regions that should never have been in contact with each other. How did distant regions of space know to organize themselves in the same way? The solution lies in cosmic inflation, a brief period immediately after the Big Bang, when space expanded faster than light. During inflation, quantum fluctuations were stretched to cosmic scales, imprinting a pattern across the entire universe before regions became causally disconnected. The cosmic web isn't just a structure that formed over time. It's the physical manifestation of quantum mechanics, written large. The web's architecture was determined by quantum events occurring at scales smaller than an atom, inflated to scales larger than galaxy clusters. Reality itself emerged from quantum uncertainty, but the evidence extends beyond dark matter into the realm of cosmic motion. In 2014, researchers discovered that our local cosmic web is moving, not just expanding with the universe, but flowing in a specific direction at 630 kilometers per second. Our entire region of space, the local group, the Virgo supercluster, thousands of galaxies spanning 500 million light years, is being pulled toward something called the Shapley concentration, the largest known concentration of galaxies in the observable universe. This implies that the cosmic web has currents. Matter doesn't just sit within the web, it flows along it, pulled by the gravity of massive structures beyond our cosmic horizon. We're not just part of a static web. We're part of a dynamic system in motion, a cosmic river carrying us toward destinations we cannot yet see. The big picture. Part A, theoretical framework. To understand what the cosmic web really is, we need to examine the theoretical framework that explains its existence. current model, called lambda cold dark matter cosmology, describes a universe where dark matter particles formed immediately after the Big Bang and began clustering under their own gravity. But dark matter is cold, meaning these particles move slowly compared to the speed of light. This coldness is crucial. If dark matter particles moved too quickly, they would smooth out structure rather than enhance it. The fact that we see a web at all tells us fundamental properties about dark matter itself. Leading physicists like Vera Rubin, who first proposed dark matter's existence, and James Peebles, who won the 2019 Nobel Prize for Theoretical Cosmology, developed models showing how cold dark matter would collapse into a web-like pattern. The gravitational attraction between dark matter particles causes them to stream toward the densest regions, creating filaments at the boundaries where streams intersect. But competing interpretations exist. Some researchers, like Eric Verland at the University of Amsterdam, propose that we don't need dark matter at all. Instead, Verland suggests that gravity itself behaves differently on cosmic scales, an emergent phenomenon arising from quantum entanglement throughout space. In this view, the cosmic web isn't made of invisible particles, but represents the way space itself is woven together at the quantum level. This forces us to reconsider fundamental assumptions about the nature of gravity and matter. Is the cosmic web a collection of particles, or is it the fabric of space itself organizing into patterns? Recent theoretical work by researchers at the Max Planck Institute suggests a third possibility. The cosmic web might be a phase transition, similar to how water freezes into ice crystals. In the early universe, dark matter existed in a hot, fluid-like state. As the universe expanded and cooled, dark matter underwent a phase transition, crystallizing into the web-like structure we observe today. This model explains several puzzling features: why the web has such regular patterns, why structures appear at characteristic scales, and why the web's properties are so similar across vast distances. Crystal structures have inherent symmetries determined by the nature of their constituent particles, and the cosmic web might simply be dark matter's crystalline form. If true, this means the universe's architecture isn't random. It's determined by the fundamental properties of dark matter in the same way that the shape of snowflakes is determined by the properties of water molecules. The philosophical implications are profound. For centuries, humans have sought patterns in the cosmos, constellations, planetary movements, cycles of time. We've imagined divine architects and cosmic blueprints. Now, we discover that the universe does have architecture, but it emerges naturally from physics. The cosmic web is neither designed nor random. It represents the universe solving an equation, finding the lowest energy configuration for its matter and energy, constrained by the laws of physics and the boundary conditions set during inflation. We live in a universe that organizes itself. Part B: Future Implications. Ongoing research promises to reveal even more about the cosmic web's nature. The James Webb Space Telescope, launched in 2021, is now observing the first galaxies to form within the web. These ancient galaxies, appearing just 200 million years after the Big Bang, show us the web in its youth, before it had time to mature into the elaborate structure we see today. Early results are surprising. These first galaxies are larger and more massive than models predicted. They formed stars more rapidly, organized themselves more quickly, and lit up the cosmic web earlier than we thought possible. This suggests the web's filaments were denser in the early universe, providing more efficient channels for matter to flow into galaxy-forming regions. The Euclid Space Telescope, launched in 2023, is mapping the cosmic web with unprecedented precision. Over 6 years, it will survey 1/3 of the sky, measuring the positions and shapes of 2 billion galaxies. This will create the most detailed map of the cosmic web ever made, revealing how dark matter and dark energy have shaped structure over the past 10 billion years. But Euclid's most important mission is measuring how the cosmic web has evolved. By comparing the web's structure at different cosmic epochs, scientists can track how dark energy has grown stronger over time, gradually overwhelming gravity and tearing the web apart on the largest scales. Recent breakthroughs suggest we might finally detect dark matter particles directly. Experiments like Xenon 1T in Italy and Lux ZPLIN in South Dakota are searching for dark matter particles passing through Earth. If they succeed, we'll learn whether dark matter is made of WIMPs, weakly interacting massive particles, axions, or something else entirely. Knowing what dark matter is will transform our understanding of the cosmic web. Different particle candidates would produce different web structures, different filament densities, different void sizes. The web's architecture is a cosmic particle physics experiment, a detector spanning billions of light years that can reveal dark matter's properties through its large-scale patterns. But perhaps the most exciting possibility involves using the cosmic web as a telescope. Radio astronomers are developing techniques to map neutral hydrogen gas within filaments using the 21-centimeter emission line. This would allow us to trace the web's structure all the way back to the cosmic dark ages, the period before the first stars formed, when the universe was filled with neutral hydrogen gas threading through dark matter filaments. The Square Kilometre Array, currently under construction in Australia and South Africa, will have the sensitivity to map this primordial gas. We'll see the cosmic web in its pure form, before stars, before galaxies, before light, just dark matter and gas organizing themselves into patterns that would eventually give rise to everything. What this means for us is profound. Every atom in your body was forged in stars scattered across the cosmic web. Every breath you take contains atoms that have traveled along filaments stretching across hundreds of millions of light years. The calcium in your bones, the iron in your blood, the oxygen in your lungs, all of it flowed through the cosmic web before collecting on this small planet orbiting an ordinary star in an unremarkable filament. We are not separate from the cosmic web. We are made of it. We are expressions of it. We are the universe organized into patterns complex enough to contemplate its own architecture. The ultimate questions, the most profound implications emerge when we consider what the cosmic web reveals about the nature of reality itself. If the universe's architecture was determined by quantum fluctuations during inflation, then everything, every galaxy, every star, every planet, every living thing owes its existence to quantum uncertainty. Quantum mechanics is often presented as relevant only at atomic scales, but the cosmic web shows us that quantum effects scale up to the largest structures in the universe. The positions of galaxies, the shapes of voids, the flows of matter through filaments, all of it traces back to quantum events occurring in the first trillionth of a trillionth of a trillionth of a second after the Big Bang. Reality is quantum at every scale. We just don't notice it in our everyday lives. But this raises disturbing questions. If the cosmic web's architecture was determined by quantum randomness, then the universe we observe is just one possibility among infinite alternatives. In other regions beyond our cosmic horizon, quantum fluctuations produced different patterns, different web structures, different distributions of galaxies, perhaps different physical laws. String theory and eternal inflation suggest that our universe might be just one bubble in an infinite cosmic foam, a multiverse where every possible web structure exists somewhere. Most of those universes would be sterile, their cosmic webs either too dense, collapsing immediately into black holes, or too diffuse, never forming galaxies at all. The fact that we exist means we live in a universe with a cosmic web calibrated for complexity. The filaments had to be dense enough to form galaxies, but not so dense that stars couldn't form. The voids had to be empty enough to allow structure, but not so empty that matter couldn't flow between filaments. This calibration seems almost impossible. Yet here we are. The unsolved mysteries and paradoxes multiply the deeper we look. Why is the cosmic web so similar across causally disconnected regions? Why do simulations match observations so precisely when we don't know what dark matter actually is? Why does the web have characteristic scales? Why 300 million light years and not 3 million or 3 billion? And perhaps most troubling, why does the cosmic web appear to be optimized for forming galaxies at all? The ratio of dark matter to normal matter is approximately 6 to 1. If it were 10 to 1, normal matter would be too diffuse to form stars. If it were 3 to 1, dark matter would clump too weakly to create filaments. The value we observe sits in a narrow range that permits complexity. Some physicists speculate that the cosmic web connects to other phenomena in ways we don't yet understand. Could dark matter filaments serve as cosmic strings, topological defects in spacetime predicted by some theories? Could the web's currents be carrying matter towards supermassive black holes that serve as junctions between different regions of spacetime? Even more speculatively, could the cosmic web be conscious, not in any human sense, but as a vast information processing network where matter flowing through filaments carries information across cosmic scales? Some researchers exploring panpsychism, the idea that consciousness is a fundamental property of the universe, point to the web's structure as potentially relevant. These ideas remain speculative, but scientifically grounded in the sense that they make predictions we could test with future observations. What we know for certain is this: the universe has architecture. That architecture emerged from quantum fluctuations inflated to cosmic scales. It's built from dark matter we cannot see, but can only infer through gravity. It shapes where galaxies form, how they evolve, and ultimately where life can emerge. And it's all connected, every filament linked to every other filament in a web spanning the observable universe and extending far beyond. The most profound implication: we can map this architecture, we can understand it, we can trace its history from quantum fluctuations through inflation to the present day. A species of conscious matter that arose within one insignificant filament can comprehend the entire web. That might be the most remarkable discovery of all. We began by asking what would happen if everything we see in the night sky is merely decoration on the surface of something far larger. The evidence has led us to a definitive answer. It is: galaxies are not the fundamental structures of the universe. They are lights illuminating the surface of a vast dark matter web, an architecture laid down in the first moments after the Big Bang, and shaped by the interplay of dark matter, dark energy, and gravity over 13.8 billion years. This web determines where galaxies can form. It feeds supermassive black holes through filaments stretching across millions of light years. It carries our entire region of space through cosmic currents toward destinations beyond our horizon. And it reveals that reality itself emerged from quantum uncertainty, that the universe we observe is one possibility among infinite alternatives. What we've learned is that the universe is not chaos. It's not random. It has structure, patterns, rules. But these emerged naturally from physics, from particles seeking their lowest energy states, from gravity amplifying tiny fluctuations, from quantum events scaling up to cosmic proportions. What remains unknown is vast. We don't know what dark matter is. We don't know what dark energy is. We don't know if the cosmic web extends infinitely or has boundaries. We don't know if its architecture is unique or if countless other webs exist in parallel universes. But the current scientific consensus is clear. The cosmic web is real. It's fundamental to the universe's structure, and understanding it is essential to understanding how we came to exist. Consider this. Every atom in your body traveled through the cosmic web before arriving here. You are connected, physically and historically, to structures spanning billions of light years. The web is not separate from you. You are part of it, a temporary pattern of matter organized by the web's architecture into a form capable of contemplating that very architecture. We are the universe studying itself through eyes made of cosmic web matter. The universe is vast. The mysteries are endless. The journey continues. But now we know. We journey along pathways written in the darkness, following threads woven at the dawn of time, connected to everything that has ever existed or ever will exist within the cosmic web, the hidden architecture that makes reality possible.